Functions that are symmetrical around the y-axis, and that'll help you know that for every intercept on the right-hand side, there will also be one on the left-hand side. Okay, today, I said yesterday that today is going to be almost the exact same thing, which it is. The only difference is, at this point yesterday, they said divide by 2, divide by 1/2. They gave you one to start with. Today they're not going to do that. You literally have to just guess about what roots might work. Well, there's something called the rational zero theorem. I've actually heard it called the rational root theorem. Sounds better to me. That's going to help you know where to look. The rational zero theorem states this. Let me ask you this. X squared, I'm just making up this example. Can anybody explain to me in words how you would factor this? What were you taught a long time ago? What did they say things to look for when you were looking to start to factor? Kim? Very good. And what else? How did you know what numbers you could factor this into? Two numbers that multiply to give you what? Two numbers that multiply to give you the end number. That doesn't change now. We are still looking for two numbers that multiply to give you the end number. So essentially, when we start looking for these in these problems, same thing. You need to list all possible factors of the end number. So like for number 1, what are all possible factors of 4? 1, 2, and 4. And they could also be positive or negative. So plus or minus 1, 2, and 4. We're going to call those our p-values. I don't know why they use p, but they do. P-values. Those are the factors of the last number, right? Well, let me ask you this. Let's take something like this. That's a bad example. 2x, still a bad example. 4x squared minus 8x plus 16. When you had to factor something like this, what were the possible, you know how when we had a normal quadratic, they all started with x and x, right? But when you have a different number up here, what are the possibilities that you could have had here in these first steps? 4x and x, what else? 2x, 2x, and then just slight variations of that too, right? Negative 4x, negative x, blah, blah, blah. Same principle. We now need all the factors of your first coefficient. Well, the first coefficient in this one is just 1. So those are called our q values. Again, don't know why. So the only factors of 1 are just 1, plus and minus 1. The rational zero theorem states that just like when you originally learned to factor, if you're going to have rational zeros to a function, meaning zeros that aren't really ugly, something like 1/2, 2, 5, something that's a nice round number, they're going to come from some p over q. What does that mean? It means I'm going to put all possible combinations of all of these numbers divided by all of these numbers, which is 1 over 1, 2 over 1, and 4 over 1, both positive and negative. So this particular function only has 6 possible zeros, 6 possible roots, period. That would be rational. That wouldn't be just ridiculously ugly like 0.3759. There's only 6 possibilities. Now, the thing for you to remember is on your test, it's multiple choice. So it's going to give you a very short list of things you can check. Now, since this is not multiple choice, I would recommend for this portion, you do use a graphing calculator. Again, it won't be necessary on a test because you only have so many to choose from. But for now, the quickest way to do this, to see which of these is a root, now if you're really good at synthetic division, by all means, try to take all those out using synthetic division, see which one gives you a zero remainder. That's actually how the book does it. But I think an even easier way, punch your function into the calculator. X cubed plus x squared minus 4x minus 4 graph. Now let's just trace these values and see if we can't find one that's a root. Trace. So let's try the positives first. Positive 1, not a root. Positive 2 is a root. Once you find one, let's pretend we couldn't just easily find all 3. Because this is what you're going to have to do on the test. Once you find one, now you can divide that out, just like you just did in your homework. So 2 is a root. So we're going to take that out of our original. 1, 1, negative 4, negative 4. drop the 1. I'm sorry, this will be a 2. Multiply, add, multiply, add, multiply, and if you did it right, you should get a 0 remainder. What is our depressed polynomial now? Very good. And you could easily use the quadratic equation to find your last two roots. And that's 80% of what we're doing today. That came from the original. 1, 1, negative 4, negative 4. Yeah. Yes, ma'am. No, but the only you can for all of these, the fastest way to do it is just punch it like actually plug them into the equation. So 1 cubed plus 1 squared minus 4 times 1 minus 4. Yeah, but see, like when we get to numbers like 5, there's going to be like 20 possibilities for p over q because we'll have 1, 2, 3, and 6, 1, 2, and 4, and you have to do all possible combinations. So now, what they're having the opportunity to have so many different combinations. That's why I'm saying calculator is the quickest way. But on your test, you know, there will only be like A, 1, B, 2, C, 3, blah, blah, blah. So you can just plug those in individually. For this one, yeah, your roots will always be the same number as your degree. And there's 3. 2 and whatever these 2 are. Now, it would be easy for us to finish this problem, but actually, we've done way too much. The only thing this problem actually asks you for is all possible rational zeros, which is this. This is technically all they wanted. I was just showing you how simple the next step would be to then find it and finish the problem. Yes. They're just all the factors of the last number, and the q's are all the factors of the first number. So like, let's look at number 5. Let's look at number 5. What are all my possible p-values? Plus or minus what? Very good. What are all my possible q values? So all my possible p over q's, plus or minus, let's see, 1 over 1, 2 over 1, 3 over 1, 6 over 1, 1 over 2, 2 over 2 is just 1, 3 over 2, 6 over 2 is just 3, 1 over 4, 2 over 4 is already covered, 3 over 4, and 6 over 4 is already covered as well. So, for number 5, the answer would be, all possible rational zeros would be 1, 2, 3, 6, 1 half, 3 halves, 1 fourth, 3 fourths, positive or negative. And that would be 16 things you had to check, which is why I'm saying today just use the calculator, and it's pretty quick. Questions about how we're getting this? P is the last number, Q is the first number, all possible P over Q's. Questions? Now let me ask you this. Before we even get to the next slide is let's just go on to it. No point in me talking theoretical when it's just one click away. Okay. 9 through 15. Part A, list all possible zeros. That's just P over Q. Do it again. Part B, once you find them, divide them out using synthetic division. Part C, once you've divided it out, take your depressed polynomial, find the other two roots. So essentially, these are the exact same as 42 through 46 on last night's assignment, with the one exception being you have to find the first one. So let's pick one and work it. What do you think? Which one do you want to work? I'm sorry? 11 you said? Alright, 11 was the first thing I heard. So here we go. Part A. Our P's over Q's. Our P's are very good. And our Q's just 1 and 2. So our possible P over Q's are 1, 2, 3, 6, plus or minus. And then 1 half and 3 halves. Excuse me. Alright. Part A is done. Part B. I need a calculator. Nope. Okay. Alright, part B. Plug your original function into the calculator. No good place for me to put this. So 2x cubed minus 3x squared minus 11x plus 6 graph. Now, we need to find one of these and then take it out. So I always just start with all the positive ones, and then if all those failed, we can go back and look for the even ones. The negative ones. So here we go. Let's try 1. Trace. 1. Not a root. 2. Not a root. 3. Found one. 3 is a root. So I'm going to take 3 out of the original. 2, negative 3, negative 11, 6. Drop the 2. 6, 3, 9, negative 2. And if you do it right, you should always get 0. What would my depressed polynomial be here? David? And David, since so many people aren't here, I imagine you can scoot up if you wanted to. Okay, that's fine. All right. Now, how do I find my last two? Quadratic. Negative b plus or minus b squared minus 4ac all over 2a. So that's negative 3 plus or minus 9 plus 8. Yuck. Yuck. Can't believe they'd be quite that ugly. But if you get something really hideous like this, then just leave it. Did I do something wrong there? Is it really that ugly? 4ac. Ugh. Oh, I'm sorry. This is 16, which makes this 25. Good. You might get ugly ones. Because think about this. Before I go on, you might think, if these are our possible rational roots and those aren't, isn't that a problem? No. This doesn't say these are only things that could possibly be. These are all the ones that you can possibly find that aren't just ridiculously ugly. So, when you get your... Okay. When you get your roots, two possibilities. Either they'll be in this list, or they're going to be ugly. Something like radical 17 over 4 that you could never possibly find. They'll either be in the list, or they won't be. So what that means is, when I do this, if I get an answer like 5, you did something wrong. Because that's rational, but it's not on my list. So anywho, negative 3 plus or minus square root of 25 is 5. So negative 3 plus 5 is 2. 2 over 4, 1/2 on my list. Negative 3 minus 5 is negative 8. Negative 8 over 4, negative 2 on my list. So your 3 roots would be 3, 1/2, negative 2. Questions about any step we took there? No. Okay. Well, I won't do any of these others for fear of boring you. I don't know why they did this. These are literally the exact same problem. You know the only difference in the direction? This one says roots. This one says zeros. But they are the exact same thing. I don't know why. I don't know. So anywho, same problem. Although, there is one on this page that's worth looking at. Notice, 23 is not a cube. It's a fourth. So how many am I going to have to find before they get down to a quadratic? Well, just until it gets down to, yeah, there's 4 total. But how many until I get down to a quadratic? 2. Now, is this an even function? No, darn. If it was, it'd be awesome. If you find one, you have the other. But it's not. So you're actually going to have to find 2 on your calculator. So first off, let's find our possible P over Q's. So that'll be plus or minus over 1. So essentially, there's just these 6. So we're ready to try it on the calculator. Clear. X to the 4th minus 2x cubed minus 5x squared plus 8x plus 4. There it is. So we need to find 2 of them. So here I go. Trace. Let's try 1. Didn't work. 2. Worked. There's one of them, but we need 2. 4. Didn't work. Now I'm going to try the negatives. Negative 1. Didn't work. Negative 2. Worked. It won't always be symmetrical like that unless it's an even function. So don't think just because this one was 2, negative 2, not always the case. Unless it was even.
Now,
So
why do you need to find 2?
because if I take just 1 out of this, it's only going to bring me down to a cube. And I can't use the quadratic equation.
Oh, okay.
Yeah. So here we go. We're going to take out 2 and negative 2. 1, negative 2, negative 5, 8, 4. Yay, it worked. Now, important step to notice here. When you take out the second, you take it out of your depressed polynomial. You take it out of that one. So, drop the 1. And you should get 0 again. And you did. And Caleb, what would be my depressed polynomial now? You got it. And from there you can just do the quadratic. It's also just a handy thing to know. What you've essentially done here is factored this into x minus 2 and x plus 2. That's kind of nifty to know. Yes, ma'am. Yep. I think the highest it'll go today is the 5th. So you have to find 3. Yes.
So is our answer going to be x squared minus
No.
2x minus 1?
We're not technically done. We need to now do the quadratic equation to find the last two. So it'd be negative b plus or minus b squared minus 4ac all over 2a. So it'd be 2 plus or minus 4 plus 4. Eesh. Now, is 1 plus the square root of 2 or 1 minus the square root of 2, is that a pretty fraction? No, it's like 1.37 blah 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 blah. Irrational, which is why it wasn't on our list. And these might also be imaginary, which would be fine too. It doesn't really matter what they are, as long as you find them. Your 4 roots, your technical answer would be 2, negative 2 from above, and then 1 plus square root of 2, and 1 minus the square root of 2. And you can find those as decimals if you prefer. It's up to you. But I'm not asking you to graph it, so. Questions? It was. If it's rational. If it was a number like 3 or 1/4, a rational number is something defined by something simply put as a fraction, whereas this is a pretty ugly decimal. Yeah. There are, I don't think you will run into it today, but I mean there are some, in fact you won't run into it in this class, but that don't have any rational ones, in which case we just don't worry about those right now. They're that ugly we don't want to worry about them. Questions about that problem or anything else on this slide? That was the hardest one on this slide. Okay. Nope. No. Okay. Question. Let's say I gave you this, and I said, what was the original function before it was factored? What would you do? You just FOIL it out. That's all this one says. It's saying, here are some roots. You know what, but I'm not going to make you worry about this one or this one. It's saying, here's some roots. Here's the power that it started with. What was the original function? We'll talk about this part in a minute. So, I know that there were 3 of them. That's what end of the equals 3 means. There were 3. And they were, well, let me go and put in my x's. Positive 1. So if my root was positive 1, what was my factor? Minus 1. Very good. Plus 5i, minus 5i. Remember yesterday we said all imaginary roots come in pairs? So anytime today they give you an imaginary root, that means they've actually given you 2. Plus that and minus that. All day. Didn't leave myself in space. So now we just start foiling. So, yes. So down here there'll be 4. Excuse me? We're going to talk about that. That doesn't come into play until the very end. So, we start foiling. It just makes most sense to me to do the last 2 together since they look to be cousins of one another. So, FOIL, x squared minus 5ix plus 5ix, cancel, minus 5i squared, well 5 squared I squared. So it'd be negative 1, 25, negative 25, minus a negative 25, so plus 25. Actually, you'll find that will always be the case. Always. Whenever you're doing 2 imaginary roots like this, it'll just be the first one plus the square of the second number. That's kind of just the way imaginary roots work. So FOIL a little further. X cubed, let's see, minus x squared plus 25x minus 25. That's when you FOIL it all the way. All the way. Now, before I go any further, we're not quite done. Questions about how I got that? Just FOILing. Okay. Let me ask you this. If this was the original problem I gave you, and I just said, what are the roots? You'd have said 1, negative 5i plus 5i, right? Does it matter what number is over here? Will that affect your roots? No. But you still have to account for the fact that there could have been a number out there. We don't know if there was a number factored out or not. So that's where this comes into play. They're saying, imagine there's some phantom number out here. We don't know what it is. But we do know that our function at f equals negative 1, so if we were to plug in negative 1 for x, it's okay. They're not very expensive. I'm sorry, I'm just joking. So if we plug in negative 1, our function will equal negative 104. And you're going to solve for that phantom coefficient. So that'd be negative 1 minus 1 minus 25 minus 25. I believe all this adds together to get negative 52, and it should always work pretty nicely like that. Now we're solving for a, so I'm going to divide by negative 52, and what will that give me for a? 2. 2 is now what this number is. That is just kind of the process you do right here. It doesn't matter if you use a, I just chose that. But we're looking for whatever this number could have been. So a was 2. So I'm going to come back and plug that in right there. So that's 2x cubed minus x squared plus 25x minus 25. Distributing that, that's 2x cubed minus 2x squared plus 50x minus 50. And there is your finished product. That is the equation that started with degree 3 with those roots. That's the equation they want. So the part at the end is just to tell you, give you the information you need to find what number could have been factored out of it. And sometimes it'll just be a 1, meaning there really wasn't one. You don't know. Sometimes it'll be a negative number. Again, we don't know. Questions on that? We can do 29 as well, but questions on 25? Foiling, then that last step. Let's look at 29. Now again, all imaginary roots come in pairs. So, what are my 4 roots here? Yes. Plus I, minus I, plus 3i, and minus 3i. What number is in front of these i's? 1. Again, the trick whenever you're foiling i's like this, it'll be x squared plus that number squared. X squared plus that number squared. Foil that out. We're almost done already. But now we need to find what could have been out here. So it's negative 1 and 20. So A equals, oh, not equals, that was wrong. -1 to the 4th plus 10 times -1 squared plus 9 equals, I guess I needed that. Was it 20? Get some more space. So that's positive. Why do I keep doing this? +1 plus 10 plus 9. What is that whole sum? So what's my A value? It's just 1. Well, when you plug 1 in here, it's not going to change anything. So this, in this particular case, is your finished product. Because 1 times all that won't change it. Questions? We're almost done. That's good news, right? Yay! Any Monty Python fans in the room? Only 2 of you? 3? 2.5?
I'll watch some of the quotes.
No, I won't waste the quotes on you then. Anyway, so no other questions about this problem? I was going to say, and there was much rejoicing. Yay. You two would have got it. Maybe 3. Okay. All right. Very simple stuff here. This Descartes rule of sign, other than in this section, I've never used it, but it's just kind of one more thing to help you. You know how we list our P over Qs to start looking, knowing where to look? The Descartes rule of signs is just something that says it'll help us know whether we're more likely to find a positive one or a negative one first. That's the whole point of the Descartes rule of signs, which I'll show you how to do in a second. It's very simple. But it's just to show you have a better chance of finding a positive one or a negative one so that you might just have a better idea of where to start looking. And here's what it is. Let's look at 33. The Descartes rule of signs says this. How many sign changes are there from one term to the next? Positive to positive, positive to positive. Were there any sign changes? No. 0. That number represents the possible number of positive real zeros. Well, how many are there total in this function? 3. And if none of them are possibly positive, then negative has to have all 3 of them. So here, Descartes rule of signs would have helped you because now you know, well, I might as well just look through my negative numbers because there couldn't possibly be a positive one. The entire function of it. However, what if they were imaginary? Imaginary ones, as we've said a few times, don't have to come in pairs, right? So there could be 3 negative, or there could be 1 negative and 2 imaginary. So anytime you get any number here, even if it was a 6 or a 5 or whatever, you have to take into the possibility that there are intervals of 2 less than that, all the way down as far as you can go. Let's look at 35. How many sign changes? 3. So that means there's 3 possible positives. How many does that leave for negative? 0. There's none. It's 3 or how many positives? You have to go down by 2s every time to count for possible imaginary ones. 1. There could have been 3 or 1 possible positives, no negative. So now you know not to bother with the negative ones. 37. How many sign changes? 1, 2. 2 sign changes. So that means there's 2 or, go down by intervals of 2. 2 or 0 positive. 2 or 0 negative. There's 2 left. These first 2 numbers will always add up to the degree. So in this case, 37 didn't help you at all. But that is it. That is the entirety of the Descartes rule of signs. No other ifs, ands, or buts. That's it. It's just to help you and to help you know where to look. Questions about where I got any of those numbers you see? I believe the last slide just puts it all together, which basically is the same as this, the last one we did. Find all zeros. Yeah, it just says use everything we taught you today and find the zeros. You all want to do 51 together? Looks like it could potentially be the rough one. And then I'll cut you loose. No, just listening. Just list them, but we'll just do honor system. Don't use your calculator because you're just setting yourself up for failure on the test. I mean, don't use your calculator excessively. Don't let it do all the work. All right, so I think it's logical to go ahead and start with our possible roots here. What are our possible P over Qs? Allie, what are they going to be? 1 and 2. So that's going to be 1, 2, 4, 8, and then 1/2, and everything else is covered. I should probably write that up here. 1, 2, 4, 8, and 1/2 are our only possible real roots. Now, let's help ourselves know where to look. How many sign changes are there? 1, 2. So that means there's 2 or 0 possible positives, which leaves how many for negative? 3 or 1. So I'm thinking let's start out looking for some negatives. No, you don't. But it could be helpful because it's really most helpful when you get like a 5 and a 0. But then you know there's not going to be any of those. So you don't have to now. I'm not going to check for it. But since we did it, I'm going to start out looking for some negatives. So bring up your calculator. On clear y equals 2x to the 5th plus 7x to the 4th. How many do we have to find on this one? We have to find 3 before we can even get it down to a quadratic. Plus 8 and graph. Whew, there it is. Okay. I'm going to start out looking for my negative ones. So, -1. I don't know. I guess we'll find out. Well, that's true. -1 didn't work. -2. Oh, darn it. -2 worked. So there's one of them. Somebody write these down for me. -2. -4. Whoa. I think we're about to get further and further away. So we must be looking at the 1 possibility for the negatives. Let's go to positive. Let's try +1. Nope. +2. Nope. +4. Looks like I'm getting ginormous in that direction too. Alright, let's try 1/2. I don't think I tried -1/2. I need to do that. 1/2 worked. How about -1/2? Darn, didn't work either. So we found 2. Negative what? 2. So we had -2 and what? And 1/2. Interesting. Is there a number we're overlooking here? I didn't do 8. That's true. It looks like it's shooting off toward infinity. That's why I didn't. We should be able to find 3. Interesting. Well, let's try this. There's 1, 2, 3, 4 that we can see. How could there possibly be another one? This shouldn't be happening. I didn't try -8, but again, that looks like it's going down to negative infinity. It won't be, because the y-intercept is 8. We found 2. This is aggravating. Well, maybe if we take out those 2, the third one we could factor by grouping or something. So, what were the 2 that I said? In 1/2. Doesn't matter which order you take them out in. Let's take the -2 first. 2, 7, -18. Whoa. Almost forgot my 0. 0x cubed. -18, -8, +8. That's 5. It's always a degree. The cube doesn't change the degree. So, what am I doing? -2. Drop the 2. Multiply, add, multiply, add. Alright, now I'm going to take out 1/2. Drop the 2, drop the 2, and -4. So our depressed polynomial at this point is 2x cubed plus 4x squared plus minus 4x 4x minus 8. That'll factor by grouping right there. But I'm very upset about, I wonder if I punched it in the calculator wrong. They should have all showed up there on the calculator. Did I punch this incorrectly? 2x to the 5th. Let me go back to the problem. Calculator. 2x to the 5th plus 7x to the 4th, 1918x squared. Mm-hmm. This should have worked. I must have punched something in wrong at a later point. But anyway, from here, this is getting embarrassing. From here, oh, I bet I know what it was. Go back. Where's the stupid graph? I wonder if this is a double root. I wonder if one of these is a double root and it just touches, but I'm not seeing it because we're not zoomed in enough. We'll find out in just a second. Regardless, let's go ahead and factor this piece by grouping. So, factoring by grouping, boom, boom. When I put it around this one, I have to remember to put the sign change. What factors out of the first one? 2x squared, leaving me with x plus 2. The next one, I can take out a 4, leaving me with x plus 2. That gives me, well, I found one of them right here, didn't I? In fact, what's one of them going to be? Negative 2. So, if you don't like factoring by grouping, you could stop here and go ahead and take out negative 2. Aha! It must have been a double root. It must have touched, but we just weren't zoomed in enough to see it. So let's take it out again. 2, 4, negative 4, 8. Taking it out of this one. Drop the 2, negative 4, 0, 0. Yep. Nope. That should be positive 8. Oh, it was negative 8. I changed that to positive 8 when I was doing synthetic. Dodge the bullet. So it brings us down to 2x squared minus 4. From there, do the quadratic formula, and you found all 5. Whew! I can't believe the first 5 when they gave you had a double root in it. That's just mean. But that's why we weren't finding it, because the same one was occurring twice. And I'm going to cut you loose, but now it's just eating at me, and I really want to see this. Zoom box. I bet if we zoom in on negative 2, I'm sorry, we're going, I know. If we zoom in on negative 2, though, I bet we see that double root much closer. Just go with it. Yep. Those snide dogs. Double root. Anyway, there you go. Yeah, 2 of them are going to be gone.